Today we're going to talk about the inverse of a function and what the inverse does. An inverse relationship says that it maps the output back to the input. So at the beginning of the year, we talked about a function, and I used an example of a vending machine. I said we've got this group of things that we can put in, and then if it's a function, we expect to get one certain thing out when we type something in. Okay? So if I go to the vending machine and I type E6, I'm expecting one thing to come out of that, and if I get something different than what I was expecting, that's not a good thing. Okay? That's the way a function works. So we've got this input, put it in, it gives us out one expected outcome. If there's more than one thing that could happen, that is not a function. What an inverse does is it turns this relationship backwards. And it says it maps the output back to the input. So it'd be like saying, oh, I just got M&M's out of here. I forgot what code I typed in. Oh, and then I look at it and figure, oh, I must have typed in E6. Okay. So an inverse maps the output back to the input. It turns the function around backwards. We have an inverse function if both the original and the inverse are both functions. So it can be an inverse relationship can happen whether we have a function or don't have a function. Just turns it backwards. Graphically, they are reflections across the line of y equals x. And that, I think, is going to be important on some of your homework problems where visually you'll want to think about what an inverse looks like. So if I have a function, let's say this function, which would be like y equals x squared, then I have this line of y equals x. I have this line of y equals x that this thing is going to mirror across. And what that means is each point on one side of the line is going to get reflected across that line. So that little part down at the bottom is going to get reflected right across the line there. So that line's acting like a mirror, like folding the paper over. And if I use paint or like really heavy pin and I fold the paper on that line, it's going to leave an imprint on the other side of the fold. And so the full inverse would look like this. Okay? That if I fold my paper together, all of those pieces are going to match up together. So an inverse and the original, when graphed together, are going to be reflections across that line of y equals x. A fact about inverses is that if we do their composition, which we learned in the last lesson, and take one function and plug it into the other function, either order, so with each of them having a term to be the outside and inside, first we'd let f be the outside and g be the inside, switch it up, then let g be outside, f be inside. Either way, we should just get x as an answer. It should just simplify straight down to x. The notation for inverse is a little -1 that looks like an exponent. I don't use the word hate very often because it's a very strong word, but I hate this notation because it looks like a power of -1. So I don't know who decided historically that this would be a good notation to use for inverse. But somebody did, and now we're stuck with it. But it looks like a -1 exponent. It is not an exponent of -1. So one way you'll be able to tell whether you have an exponent of -1 or whether it's meaning an inverse is if this is happening on our function name. So if it's on an f, it doesn't mean f to the -1 or 1 over f. Okay? It means inverse. Or if it's happening, typically our function name could be like a y equals. If it's happening on a y, it doesn't usually mean a 1 over y. It usually means the inverse of y. But I think it's kind of a poor choice for notation. So first, how do we find an inverse? To find an inverse, we have two steps. First thing we're going to do is switch x and y, because what an inverse is it says it maps the output back to the input, or it switches up what is out and what is in. X and y are what represent the ins and the outs of an equation. So we're going to switch them up. So I'm going to swap x and y in the equation. And our second step is get y alone again. Add 4 to both sides. And divide by 2. I don't really want to call this y because I already had a different equation that was called y and it was different. This is something new. So then that's where we would want to bring in that inverse notation and say this isn't y because we already had y, that was the original problem, but this is related in that it's the inverse of the original one. Okay? So that's our answer. So switch x and y in the equation, get y alone again, and then tag that notation on there. And always at this point, somebody says, if I forget the notation, are you going to mark me wrong? I'm probably not that mean, but I would really like you to try to remember to use appropriate notation. Okay.
So that's our answer.
So that's our answer. So on this one, switch x and y. And then get y alone again. So subtract 6 from both sides. And divide by -3. When we do our divisions or our multiplications, make sure that you're doing it to every single term of the equation. Everything that hits a plus or a minus, you need to divide or multiply again. So I get x over -3. Negative or negative plus 2 equals y, and I'm going to call that y inverse, since it's different than the original y. Questions on how to find an inverse? Okay, our next questions are going to say verify with composition of functions. So that's what we learned on Friday, that we have inverses. What we're going to do is plug them into each other, letting each of them have a term being the outside and each of them having a term being the inside. The answer should be x, which means that in these problems, I'm telling you the answer is x, which means that writing x and putting a box around it is not going to cut it for your answer. The work is the answer on these problems. On a verify problem, I hesitate to use this word since so many of you strongly and vehemently dislike them, but it's kind of like a proof that it's the work that matters. It's not the final answer. I'm telling you the answer will be x. It's the work that gets us to that answer that matters. Okay? So what we're going to do is let each of them have a turn being the outside and the inside. And when we did this on Friday, I kind of color-coded it to help us see what was happening. So first, I'm going to do f of g, f prime of x, or f inverse, sorry, of x. So we learned on Friday that to do a composition of functions, you write the outside function, which this time is the purple one, except don't write the variable and leave a blank. Then in that blank goes the inside function. And then we need to clean it up and show that we do get, in fact, an answer of x. So I'm going to distribute the 2. And I get x plus 4 minus 4, which is x. Then we're going to switch them. So this time the inverse is on the outside and f is on the inside. So to do our composition, we write our outside function, leaving a blank for the variable. And in that blank, put the inside function. Distribute to clean up. So I get x minus 2 plus 2, which is x. So for these problems on your assignment that say verify or show with composition, I'm telling you the answer will be x. You have to actually show the work of both ways of composition, letting each function have a turn to be the outside and be the inside. Okay. All right. So, do one more example like this. So first I'm going to let f be the outside. So I write that outside function, but leave a blank where x was. So instead of 3x plus 6, or negative 3x plus 6, it's just negative 3 blank plus 6. In that blank goes the inside function. Distribute gives x minus 6 plus 6, which is just x. Then show that it works the other way as well, putting the inverse on the outside and the original on the inside. So I write negative 1/3 blank plus 2. And in the blank, put the inside function. Distribute gives x minus 2 plus 2, or just x.
So what would we show our answer? Like what would be our final answer?
All of that. Yeah, there isn't like a final answer because the final answer is x, so I'm telling you that.
Yeah.
So it's really all the work that just needs to be shown. So like exactly what's on the screen would be what I would want to see.
Do we have to write like that? Like do we have to write that part?
I guess you don't have to show the composition part, but for me it helps me remember what's being inside and what's being outside, but you don't have to, I suppose. The horizontal line test. Earlier this year we had a test that was called the vertical line test. What did the vertical line test tell us? If something's a function. So earlier this year we studied the vertical line test, and the vertical line test told us if we have a function or not. So it said, look at your picture, and if you draw vertical lines and you ever hit more than one point, it's not a function. So this one is a function. Okay? And this one is not a function. Because if I draw a vertical line, I'm going to hit more than one point. Okay? So we studied vertical line test earlier this year, and it told us whether the graph is a function. The horizontal line test tells us if that inverse will be a function. Okay? The horizontal line test tells us if the inverse will be a function. So if I do the horizontal line test on this, I'm going to fail the first one, which means that the inverse is not a function. On the second one, if I draw horizontal lines, I'm not running into any problems, so that means the inverse is a function. It is possible for both a function or an original and its inverse to both be functions. So, for example, if it's just linear, that passes both the vertical and the horizontal line test. So both the original and the inverse would be functions. Okay? Vertical test the graph itself. Horizontal test the inverse of that graph. Okay. This question asks us to find the inverse of the function. So, like our first problems, we said to find an inverse, we're going to switch the x and y. Now this one doesn't have any y's in it, but it does really, kind of, it just doesn't look like it. Where's the y? F of x means the same thing as y. F of x is just another way of saying y. So really there is a y here, it's just using a different notation. So our first step to find an inverse is to switch the x and y. And then get the y alone again. So how do I get the y alone? Square root both sides. What do I need when I take a square root in an equation? Plus or minus. Except we have one piece of information here that we haven't dealt with yet. And that tells us that we're only dealing with positives, which means we only need the positive root here. So we don't actually need the plus or minus. If it said x is less than or equal to 0, then we'd want to reevaluate the problem for that. But careful with your even roots. If it doesn't give you any specification, you need some pluses and minuses. So for this one, switch the x and y, remembering that y is f of x. Those mean the same thing, it's just a different notation. So switch them. X equals y to the fifth. And take a fifth root. Do I need a plus or minus?
No.
Why not?
Well, it's not square root.
It's an odd root. Okay. Even roots we need to think about plus or minus. Odd roots we don't need to think about it. So that's our answer. Now really if we want to be perfect on notation, we shouldn't have a y there because the original didn't have a y. So we should do f inverse of x if we want to be perfect on notation there. Again, am I going to be super picky about that? Probably not, but I would like you to at least try to use proper notation.
So like the last one we did.
The last one should have been as well. Alright, and our last type of question says, will the inverse of the function be a function? And then find the inverse either way. To tell if we're going to have a inverse that will be a function, we are going to graph our original. You can graph it on the calculator if you would like, either a graphing calculator or a graphing calculator app. You can graph the function that's given. When you graph this one, it's going to look like this. So we're going to graph the given function, and then we're going to use the horizontal line test. So the horizontal line test says, if I draw horizontal lines across this thing, am I ever hitting more than 1 point? No. That means the inverse will be a function. So don't do the graphing by hand. It's fine to graph them on your calculator or on a graphing calculator app. So graph the given function. Look to see if a horizontal line will ever hit more than 1 point. If it does hit more than 1 point, the inverse will not be a function.
So we don't have to draw the graph.
You don't have to draw it out. You can just look at it and it's fine. Then it asks us to actually find the inverse as well. So to find the inverse, we want to switch the x and y, remembering that f of x really means y. So this is going to become x equals 1/2 of y cubed minus 2. And then get the y alone. What do I do first to get the y alone? Add 2. And then multiply by 2, and make sure you multiply the entire equation by 2. We need to multiply each and every part of this by 2. So we get 2x plus 4 equals y cubed. And then cube root. Do I need a plus or minus?
Nope.
Why not?
It's an odd group.
It's an odd root, so we don't need plus or minus. And then again, just switching out our inverse to back how we started. Since we didn't start with y's, we probably shouldn't end with y's. And this is the inverse of the original f. So we do that little -1 notation. Same type of problem. First thing we're going to do is graph the given function. It looks like this. And then do the horizontal line test. Does this pass the horizontal line test?
No.
No, I am definitely hitting more than 1 point when I cross it. So that means inverse is not a function. If we draw a horizontal line, hit more than 1 point, that means the inverse will not be a function. It does still tell us to find the inverse anyway. So I'm going to switch the x and y. And then what do we do first to solve? Add 4. And then divide by 2 and make sure you divide every part by 2. You get x over 2 plus 2 is y squared. And then square root it. Do I need a plus or minus?
Yes.
Yes. And that plus or minus is actually what makes this thing not be a function. That plus or minus is actually what ends up causing us the problem.
So when it's square, you do the plus or minus.
Anytime it's an even root, so a square root or a fourth root, then we would need a plus or minus. Okay, and your assignment is from 7-4.